Okay, so I'm going to be trying to explain the concept of Michaelis constant and the concept of Vmax in a most simple manner possible. So we're first going to look at what Vmax is. So Vmax is the rate of reaction at enzyme peak saturation. So this means, what this means is, let's say there are 4 enzymes present in a solution, just for simplicity's sake. Let's say you have 4 substrates, and when all of these substrates are bound to the enzymes, we look at the rate of reaction and the value of it, and that is what Vmax is. So how fast the reaction is going when the enzymes, all of the enzymes, are bound to substrates. That's what Vmax is, okay? And the keyword here is peak saturation. All of the enzymes have to be bound to substrate. Now, just keep in mind, in practical situations, this is not going to happen because there's always going to be some enzymes, maybe at the side, that won't bound to substrate for whatever reason. Maybe there is too high of a pH, or maybe the shape doesn't fit. There are a number of factors that can influence that. The next thing we're going to look at is called the Michaelis constant. So Michaelis constant. Now what this represents is the substrate concentration at half of Vmax. Or in other words, it's how much substrate is needed to reach half of Vmax. So I'm going to write this again. So substrate concentration that is needed to reach half of Vmax. Or what does half of Vmax mean? So let's simplify this further just to clarify. Half of Vmax is the rate of reaction at 50%, so half of an enzyme peak saturation. So when half of all enzymes, so let's simplify this even further, so 50% of all enzymes saturated. Okay, so when half of all enzymes are bound to substrates, we look at the rate of reaction, how fast the reaction is happening, okay? And in order to reach the reaction, we need a certain amount of substrates, which makes sense, right? How much substrates are needed to bind to half of all enzymes, right? And that is the Michaelis constant. The units are going to be in moles, all right? Because this is basically giving you the concentration of the substrate, while Vmax, its unit, is going to be moles per second, or moles per minute, or moles per hour, or so on and so forth. So now that we got these two terms defined, now we're going to apply these terms to describe inhibition. So there are a number of factors that can influence both of these values. So I'm just going to erase all of this here. So it can either be affected by the pH, notable examples of pH influencing enzymes is pepsin. Pepsin is a digestive enzyme, therefore it's going to be in the acidic environment. Pepsin, and this might come up in maybe school assignments or whatnot, but pepsin is actually, it's an activated form of pepsinogen, right? Pepsinogen is a precursor to pepsin, and pepsinogen is commonly referred to a category under zymogen. So it is zymogen. So zymogens are, if you go to the word origin of it, is actually Greek. So zymo in Greek is enzyme. Sometimes I find it helpful to break these terms down into Greek origins. So gen is actually to produce. So zen is to produce an enzyme. So zymogen, pepsinogen, right, is a zymogen, is a precursor. It needs to be activated in order to become pepsin, right? And how does that become activated? It becomes activated by the low pH, around 2 usually. So because it's a digestive enzyme, we don't want it to be activated all the time, right? And so when it enters the stomach is going to have all that bile and acid, and that makes the environment acidic. And so when pepsinogen enters the stomach, it's going to go into the acidic environment. It's going to react with the protons, and that is going to become activated in a pepsin form, and the pepsin is going to be able to go and get involved in the metabolic processes. All right. So pH is a factor that can influence it. Another factor that can influence it is temperature. Now, there's a warning here. Higher the temperature, usually the case is that reaction goes more faster. It's like the reaction gets all riled up, and if the temperature goes up, it's happy. There's more, more molecules bouncing around, and they can meet each other. But if the temperature is cold, the kinetic energy is going to be down. It's not going to be happy. It's going to be sad, right? And it's going to actually move away from each other more frequently. So that's why hotter temperature usually leads to faster reactions, but that is not always the case. It's just a typical scenario, right? And another factor is inhibitors. So for inhibitors, so I'm actually going to move all of this down. So inhibitors, now I want you to classify inhibitors in these 3 categories. So first category is allosteric inhibition. And what this is in an enzyme, there are 2 sites. So maybe this site is active site. All right, this is where inhibitors usually bind in competitive binding. And there's another site here. It's called allosteric site. And in allosteric sites is where inhibitors can bind to influence the enzymatic activity. Okay? And the allosteric inhibition encompasses 2 things. So there's a competitive allosteric inhibition, and there's non-competitive allosteric inhibition. All right? So in competitive allosteric inhibition, it's going to bind to the allosteric site, and it's going to prevent the substrate from binding. So the substrate is going to try to bind. So I'm going to depict it as this small molecule here. It's going to come in, it's going to try to bind to this site. There is no inhibitor present at the active site. However, the inhibitor binding to the allosteric site is going to change the conformation of this active site. So it's going to change this to maybe it needs to be a circle, but instead it's going to be changed to a star because the inhibitor bound to the allosteric site. So now this substrate isn't going to be able to bind, right? Although inhibitor is not at the active site. So and the non-competitive allosteric inhibition, in contrast, right, it's going to bind. The inhibitor is still going to bind at the allosteric site. However, the substrate is going to be able to bind to the active site. So the substrate is still going to be able to bind. However, the enzyme itself isn't going to be able to catalyze a reaction anymore because it changes the function of the enzyme. So in competitive allosteric inhibition, the substrate comes in, it can't bind. And in non-competitive allosteric inhibition, the substrate comes in and can bind, but the enzyme can't carry out its function anymore. All right? And there's another category. It's a whole other separate category, which is competitive inhibition. All right? So competitive inhibition is the same thing as competitive allosteric inhibition, except instead of the allosteric site, the inhibitor binds at the active site. So the substrate isn't going to be able to bind to the active site. All right? It has almost the same effect as the competitive allosteric inhibition. However, in competitive allosteric inhibition, inhibitor binds to the allosteric site, while in competitive inhibition, the inhibitor binds to the active site. All right? Okay. So now we're going to look at how the inhibition affects the Michaelis constant. So how does this exactly, relate to Vmax and the Km, the Michaelis constant? Okay, so we're going to go back to Vmax. So that means rate of reaction at peak enzyme saturation, right? And Michaelis constant is substrate concentration needed to reach half of Vmax, or half of total enzyme saturation, right? So how does what we just discussed, the inhibition process, the non-competitive binding, the competitive binding, how does that relate to this? Well, okay, let's go through competitive binding first. right? Competitive inhibition. That is when the enzyme, let's say this is the active site, right? And the substrate can't bind because the inhibitor is already there, right? It's like, I don't want you here. This is my house now, you know? So the substrate is going to be very unhappy. In this case, the Vmax is not going to be affected. It's going to be not affected. But why? How does that not get affected? You just said that changes the enzyme binding. Yes, it does prevent the substrate from binding. However, you can increase the amount of substrates, and that will eventually outcompete the inhibitor and essentially just kick it out. Oops. So the inhibitor is going to be here. It's basically like, you know, when the substrate comes alone, it's going to be like, it's my house now. You can't do anything about it. So the substrate is going to bring more friends. You know, it's going to bring more friends, and the inhibitor is going to be intimidated and it's going to leave. You know, so what does this mean? This means that the rate of reaction at peak enzyme saturation is not going to be affected because the enzymes can still be saturated. It's just going to take more substrates. And notice how I said more substrates. So more substrates are needed to reach Vmax. What does that mean for Michaelis constant? Michaelis constant, if we go back, it says substrate constant needed to reach half of Vmax, right? So if we need more substrate concentration to reach Vmax, it just makes sense that we're going to need more concentration of substrates to reach half of Vmax, right? So the Km, the Michaelis constant, is going to be affected, and it's going to increase. The substrates that we need to reach half of Vmax, the amount of substrate that we need to saturate half of total enzymes, are going to increase because we have to outcompete the inhibitors that are bound to the active site. We have to bring more friends to intimidate the inhibitor, right? Now let's look at non-competitive inhibition. Just a note, this competitive inhibition, this also includes allosteric competitive inhibition, right? Remember what I said about allosteric competitive inhibition? It's when the inhibitor does not bind to active site, but it binds to the allosteric site. But that still changes the conformation of active site, so it prevents the substrate from binding. However, it can still be saturated, just like competitive inhibition. You just need more substrates, okay? For non-competitive inhibition, however, it's going to be a little different. Why? Because in this case, right, in non-competitive inhibition, well, the inhibitor is going to bind to the allosteric site, right? And the substrate it comes along, it sees the active site, and the inhibitor is going to let the substrate bind to the active site. Why? Because it's not concerned with the substrate, it's going to be concerned with the enzyme. The enzyme is not going to be able to carry out its function. Now, what does this mean for the rate of reaction? What does this mean for the Michaelis constant? Well, let's think about this. So Vmax, right, is that going to be affected? Yes, it's going to be affected in this case because, as I said before, it lets the substrate binding, but the enzymes cannot carry out its function. What does the Vmax mean? It is the rate of reaction at peak enzyme saturation. So the Vmax measures how fast the reaction is going. And if the enzymes cannot carry out its function normally, the rate of reaction is going to decrease. So the Vmax is going to decrease. That makes sense because if some enzymes can't carry out its function, the number of enzymes that can catalyze the reaction, that can push the reaction forward, is going to reduce. And that correlates with the speed of reaction, right? So it makes sense that Vmax decreases. How about the Michaelis constant? For the Michaelis constant, well, it lets the substrate bind, right? So the substrate can still bind to the enzyme, and the Michaelis constant is only concerned about the substrate and the enzyme binding, and it still happens. It happens. It's just the enzyme can't carry out its function. The substrates don't bind, so the Km is not affected. The Michaelis constant is not affected because the substrate concentration that's needed to reach the half of enzyme saturation, so half of total enzymes that are going to be saturated, is still going to happen. The substrate is still going to bind, right? Does that mean the rate of reaction is going to be the same? No, because the enzyme can't carry its function, right? So to summarize, I'm just going to make a little summary chart here. So to summarize, right? If you see competitive binding, competitive inhibition, that is going to affect the Km is going to increase, but the Vmax is not going to be affected, All right, for non-competitive inhibition, the Km is not going to be affected. The Vmax, however, is going to be decreasing. All right. And now, one more thing that I want you to remember is, like this. Basically, Vmax is going to be concerned with the reaction and reactions rate and the enzyme saturation. All right, it's going to be concerned with these two things. And for Km, the Michaelis constant is going to be concerned with substrate affinity with enzyme. All right, how well the substrate binds to the enzyme. So just remember this page that I've drawn here, and you'll be okay. And I hope that explains what Michaelis constant and the Vmax is.